Hello again, YouTube. Sorry for a huge delay, but busy with a contract, so haven't been able to get to this as often as I'd like. Hopefully now getting into the rhythm of it again and be able to find time for this. This is a brand new project. You can't open enough projects or start enough fresh projects. I was given this board by somebody who has a very fancy light system with it's actually kind of a light with three different light arrangements on it. One points up, one points down, and one's kind of a spotlight in the middle. That's neither here nor there. This is the control board which is causing a problem. It doesn't actually work. So I had a look at it, and there's a huge big scorched area there which corresponds to this big, it's a bridge rectifier, and I could possibly find a replacement part for that. It probably is standard, but I think I might just redesign a board as kind of almost like a learning thing, because I've never dealt with this before. I mean, all we have is an 1890 microcontroller. Now there's three circuits to control the brightness of the three lights. So you've got mains coming in through this side, and then this is three pairs for each of the three lights. So it's quite, on the face of it, quite simple. I mean, this is old technology, and even this capacitor has been soldered onto the lead of one of the resistors. So it's kind of a botched job. I don't know what. Now, I did get in touch with the company that make this light, asking about replacements. I've contacted them a few times, but they've never actually responded. So obviously they're in the business of selling lights and not doing much in after sales service. So anyway, it's a project. Now, the one thing that the owner wants is to be able to use this remote control again. So the remote control it's actually good, because the remote control board, or the receiver, is in this little extra PCB which plugged into this little connector here, this 4-pin connector. So I can reuse that. So instead of having to try and find an infrared receiver which is operating at the same wavelength of light as these transmitters, I can actually just use that small PCB with the infrared receiver and the connector as well. I'll probably desolder that connector and just reuse it, although it doesn't seem that the locking tab has disappeared. Nothing to do with me, obviously, but I don't know where it's gone. But look, so the connector isn't perfect, but it'll do. So there's a number of elements to this. I need a zero crossing detector to switch on and off, switch these lights on when the AC signal is crossing zero. Now there's a couple of YouTube videos on that. I'll link those in. I'll do that in another video. This time I'm just going to concentrate on the remote control transmitter and the receiver, and trying to, if we're going to use these two pieces, we have to understand and be able to distinguish between the 9 different buttons here, and be able to distinguish them and read them into a microcontroller. So we'll do that in this video, and hopefully in the future I'll come back to the zero crossing detection. And zero crossing detection is one part of it, and then the actual output here to turn the actual mains on, because whilst the microcontroller is going to be at a low DC voltage, it's actually, we're going to be switching mains voltage. So I'm in Europe, so it's 240 volts at 50 hertz, and that is going to be switched out. The microcontroller is going to control it, but it's ultimately going to be a mains output. So now, in order to test this out, to investigate what is the output from the transmitter to their infrared receiver, I've just soldered up a little Vero board with, now I'm powering this receiver with 5 volts, and I've got the Cinnamon Bun is a DS PIC 33, which is running at 3v3, so I've got just a small voltage divider resistors there, and that's all this board pretty much is. Like I'm taking the input from the infrared receiver into D0, and I've got it on the logic analyzer here, channel 0. This other pin, I was using that for test, but the only other pin of the 4, there's ground, power, the output from the infrared receiver, and the other one was control of this LED, so you could flash this LED, turn that LED on and off. We won't worry about that for the minute. So what we want to do is look at this in pulse view, and if we just look at D0, and we could trigger on so if we now trigger on a downward pulse, if I push one of these buttons, we should see, if I run it, we should see, push a button, yeah. So we now have to decode this logic. And if we look at these pulses, this looks like it's idle high and then gets pulsed low for a short period of time, goes back to high and then low again, and this is happening 8 times. So I've looked at looked into a few protocols used by infrared receivers, can't see something like this, but it just looks like this is a start bit and stop bit, start bit, stop bit, and repeat it 8 times. And then the difference between the start and the stop bit, or the duration in between, so if we zoom in on that start bit and stop bit, the duration between the two is different from those two there. So if I roughly bring up a cursor and say that's a start, that's a stop, just zoom in again, look at a time. So that's roughly 2 milliseconds. If I zoom in again, maybe I'll get a more accurate time. 1.9 milliseconds. Whereas the next start and stop bit is roughly 2.3. So we've gone from 1.9 milliseconds to 2.3 milliseconds, and that is the difference between those pulses. And that is repeated. So I've got those 8 bits make up the byte, and it's repeated again because I wasn't quick enough taking my finger off, and it's the same pattern again. Start, stop, 8 times, and again. So now all I've got to do is build this into the code of my microcontroller. Unfortunately, the one thing I've never included in the libc library of code for the DS PICs, or the PIC24 for that matter, is the fact that I start timers for, I have timers for, if I go to the top of this file, I've always had API functions for creating hardware timers that expire, and then there's a callback. So we send in a timer request structure with a time that we want to expire, and then there's a callback function associated with that. So that structure contains the period, which is the duration that we want, and the timer type was always a single expiry or repeated expiry. So we want the timer to go off every second or every 500 milliseconds, and that is the function we want called the callback function. So this is an event-driven system. The timer becomes an event-driven system, and this is the data that we would like passed to the expiry function, if there is any data. It's usually null. I've never really had a reason to pass data, but you can pass data. So I've never had something which would solve this problem of measuring the duration of this start-stop. So I've had to add that into my API, and to do that I've just added a new timer type. So as well as the single shot expiry and the repeat expiry, we've got a stopwatch expiry. This code isn't indented properly because I've probably recently installed and I usually use Linux. So I've added a new timer type to a hardware timer. So now all my main does, because I want to detect the duration of these pulses, both the start pulse, then this long idle period, and the duration of the stop pulse. All my code does, this is all operating on D0. So I set D0 as an input and add a change notification. So we want to be notified of a change, and this is the function we're going to call is this change notification. Anytime D0 goes high to low or low to high, we're going to get this, that function is going to be called. So this becomes event driven. So then that function, whenever there's a change, it simply stops a stopwatch timer. So we're going to create now one of these hardware timers, which is a stopwatch timer. We're going to start it and stop it and restart it. So in main, we just set up our stopwatch timer request. So we're going to measure in tenths of milliseconds. I've added this. I previously only had microseconds and milliseconds, but I've added tenths of milliseconds because that makes more sense in this, because the two times we had here for the different pulses was 2.3 milliseconds and 1.9 milliseconds. If you actually measured that in milliseconds, it'll probably both come out as 2 milliseconds. So there's not enough of a difference. So I just added a new period units of tenths of milliseconds. So we want a stopwatch timer in tenths of milliseconds, and that just initializes that request structure. Set up the change notification, and then just drop into lib e-tasks, our infinite loop measure and e-tasks, and this should be an atomic operation. All the change notification does, because the change notification is going to be executed on an interrupt level by the microcontroller. So we want to do as little as possible in here. So all it does is stop the stopwatch timer and restart it. And the call to stop accepts as its parameter both the timer identifier and a period, and that will be filled in by the call to stopwatch timer. So when you call that, the period that you get back, pass in a pointer and you'll get back the actual duration that the timer's been running for. So what we're going to do is when this pulse goes high, we stop the timer, restart the timer, and there'll be a duration there. And then when we get to the end, to the stop pulse, we call stop again, and we have a duration stored. And then the timer will be restarted so we can measure the duration of this stop bit. And because this is an interrupt service routine, or at that level of execution, we want to do as little as possible. So all we do is stop the timer, start the timer. If there's an error, then we can actually waste our time faffing about printing out stuff, but otherwise we don't want to print anything. We want to get in and out of this function as quickly as possible, and we increment. And this should be an atomic, but my API doesn't have an atomic. What I mean by atomic is that you don't want this to be written to and read at the same time. You would protect this with semaphores, so that this interrupt service routine is incrementing that value. Our main loop in the code down here is waiting for it to be positive, and when it's positive, it knows there's been an event, there's been a change, and we want to execute. So we would execute and subtract. So I could actually probably best move that up there. You don't want the two to be executing at the same time, because we could go into this. It's simpler in this case because one is doing an addition, the other is doing a subtraction. There's not much of a conflict. But in some cases, if two pieces of code were doing addition or subtraction, then you want to make sure that only one can do a thing at a time. So you protect that date element with semaphores, and I haven't got around to doing that, but in this case I don't think it's going to be an issue, but it should be atomic, so I've just called the variable atomic. So anytime the atomic value is positive, there's been a change, then I handle it in a state machine. And the state basically mimics where we are in this. If we're waiting for a start bit, then we're in a state that represents that. If we've got the start of a start bit, then we change state again. And that's all. The rest of the code is just these states. So we've got a state here that's awaiting the end of the end pulse. So the one that's different is in the idle state, we're waiting. Once we get a change and we go we've gone low, pin D0 goes low, then we've got the first start bit of a byte. So we've gone into this awaiting state. We've got a low pulse. Now we're awaiting the end of the initial start pulse. And when we get the end of the initial start pulse, obviously D0 has gone back high again. We want to start a timer. If the duration of that pulse is the correct length, so that start pulse the start and stop pulse are both about the same, and we want them to be about 300 microseconds. So if our start pulse is that value, is in that range, plus or minus a threshold, then we're waiting. We're in the starting. We're now reading a bit, the duration in between, this duration here, and we're awaiting an end pulse. So we're waiting the start of the end pulse. And we start a timer to time the end of the byte. So we want to receive this pattern. We've got the first start pulse there, and we want to keep measuring until we get to somewhere there, 50 milliseconds. And that's what we expect the byte to be. So we start a timer for 50 milliseconds, and when we've got the initial start bit, we go 50 milliseconds, and then we'll expire on this expiry function, the end of the byte. And all the end of the byte does is print out, we'll store the values that we get. So once we've got a start pulse, we go into awaiting the start of the end pulse. When we get the end pulse, this is where we've got the end pulse. D0 has gone back low, and either we've got a 1 depending on the period, or we've got a 0 depending on the period. And we just shuffle that into this RX data, and that becomes our value that we're reading back from. So now if we just look at the output of this, if I set the speed, usually 19K2, carry a watch off and connect. So now maybe if I reduce the size of this, and push a button. And this is now what we're measuring, and this is in tenths of milliseconds. So we've got about 0.3 of a millisecond is the start pulse, and 0.3 is an end pulse, and 1.7 milliseconds is that pulse. So we're interpreting that as a 0. So the first pulse is 0, the second pulse is 2.2 milliseconds, back to 1.7, 1.8 there, 2.2, 1.8, 2.2. It's not extremely accurate, but it doesn't have to be totally accurate. I mean, it's good enough to be able to tell the difference. This is 0x55. Now, these buttons may have been like we might be interpreting this the wrong way. I mean, we might be interpreting a 0 as a 1 and a 1 and a 0, but it doesn't matter. We just have to be able to tell the difference between the button presses. So if I bring up if I reduce this and look at these, so we've got these buttons here were presets. So 1, 2, 3, 4 down the side was you stored values for the various lights. So if I press 1, I get 55, 2, 66, 3, 77, 4 is 88, that led 22, 33, 44, 99, and the on off button, the last red one, sorry I'm drifting out of frame, is 11. So that's it. This is the first step in trying to replace this board. I now know that I can use this infrared remote control and this little LED receiver, infrared receiver. I don't have to worry about wavelengths of light and all the rest of it. I can just use those as is, and now try and replace this board with the necessary to be able to switch in AC mains, and we need zero crossing as well. So that's another video another time. Meanwhile, I'll have to, this API for stopwatch timers in the hardware timers, I have to now commit that back to the libsoup on GitHub it's maybe not perfect, but it'll suffice for the moment. These things, this API, this library of code will actually be augmented when you hit a problem that you can't solve with the current code. Then you have to add code to it, and this is the first time I've needed stopwatch timers. I could have used it earlier on in the series of videos I started with Morse code, and to actually listen to or interpret Morse code, you've got to be able to measure the duration of a pulse and be able to say, well, that's a dot or a dash, depending on the duration. And I could have used it then, but I kind of never got round to completing the Morse code stuff. I'll leave it there for now. I'll commit this back to GitHub, and I might throw this project. It's not really a useful project, but it's an example of how you would use a stopwatch timer. Just by having this change notification. Now, one of the holes that we have is this atomic value. Like, if you looked into the code for the Linux kernel or something, there would be, if you create a data type which is atomic, you'd have like I've declared that as a uint8, but in something like the Linux kernel, you would have an actual type, which on the face of it is an 8-bit integer or whatever, an 8-bit value, but it is protected by you when you add or subtract to it, it's protected so that only one process can do that at a time. Now, we don't really have a multiprocessing in this microcontroller, but we do have interrupt level execution and normal execution. So this can be running along, and the test here is that we read the value of atomic, and if it's 1, then we go into this part of the code. But if we read that value of the atomic and then get interrupted, then we can read 0, but then a moment later. It's not a problem in this case, but it can be a problem in other cases where you've got multiple people or multiple parts of the code accessing that data type. I'll leave it there for now. Thanks a million for watching, and sorry for the long pause between videos.